Okay, so now last time we completed chapter number 2, and that was about introduction to conduction. And the introduction to conduction in the sense that we developed one of the most important and fundamental equation, which is the heat diffusion equation. We developed it, we derived it, we proved it for Cartesian coordinates, but we said that for the cylindrical and spherical coordinates we are going to directly use the results. Okay, so now we are going to continue with it. Okay, so let's have a recap of just the equation. What was the equation? So it was q dot plus it was k initially d dawa by dawa x, k dawa t by dawa x, right? Then dawa by dawa y, k dawa t by dawa y, then dawa by dawa z, k dawa t by dawa z equals to rho Cp dawa temperature by dawa time, right? So that was the fundamental equation in Cartesian coordinates we did. Okay, now this chapter number 3 is about, now read the name, one-dimensional steady-state conduction. When we say one-dimensional, what does it mean? So it's y and z cancel. Okay, normally we consider one dimension as x. Okay, so y and z cancel. Okay, so that means this chapter we don't have these terms, and it is a steady state, so no change with time. So there is no change of temperature with time, so this term is also not there. So this chapter we deal with this thing, q dot dawa by dawa x, k dawa t by dawa x equals to 0. Okay, now the thing is that we are not going to deal with the cases where we have non-isotropic material. Only we are going to deal with the metals, and most of them are isotropic. So k is a common, is independent of direction, can come out. So we have q dot plus k. Okay, now since it's not dependent on y, z or time, so we, instead of writing dawa, I can write d, because it's dependent upon only one thing, d square t upon dx square equals to 0, right? So now this is the equation which we are going to deal in this chapter, one-dimensional steady-state conduction. Okay, so what we are going to do is that we are going to start step by step. First, we are going to deal with the case when there is no internal heat generation. If there is no heat generation inside, so that means this thing is 0. So first we are going to start dealing with this thing only. Once we have developed all the equations related to this thing, then we are going to add heat generation. It is going to make the problems more complicated. But anyways, we're going to do like this. But this is the equation that we are going to deal with. This is the name of the chapter, one-dimensional steady-state conduction. Okay, that was the fundamental equation we developed in chapter number 2. This is the equation which will become the basis for chapter number 3, 4, and 5. So for chapter number 3, simplifying, it becomes this. Is it clear? Okay. So these are just, because chapter number 3 is a very big chapter, and in reality we are not going to cover the complete chapter. There are some topics that we are going to leave behind, we are not going to cover. So what are the things that we are going to cover? It's just written in the next 2 slides. These are all just the topics name written and what are we going to cover. Okay, so let's move ahead. Okay, so conduction for a plane wall. A plane wall means a regular wall, like this, plane surface, no curvatures, nothing, just a wall. Okay, so suppose we have a plane wall, but as I told you, initially we're going to start with no internal heat generation. So q dot is also not there, is 0. Okay, so this is the equation that we have. So now we are going to start from here, and we have to further solve the problem. So suppose we have a plane wall, and the plane wall is like this. This is a plane wall. Okay. Now this is a differential equation. This is a differential equation, and it's power 2. Okay. So in order to solve the problems, we need the boundary condition. In order to solve this equation, we need boundary. Why are we solving it? What is basically here? What does this equation tell us? This equation tells is that temperature is varying with distance, right? And when we are going to solve this equation, we are going to find temperature as a function of distance. So if we solve this equation, we will get temperature as a function of distance. That will be our answer. This is what we need. Okay? We need temperature as a function of distance. So our objective is basically, if we have a wall, we need to know what is the temperature at all points in the wall. Okay? We need to know what is the temperature at any point in the wall. That's our objective. Because the thing is that if we know the temperatures, then we can decide what is the amount of heat transfer. Because the amount of heat transfer depends upon the temperature. Okay? So we need temperature field to know the heat transfer. So by solving this equation, our objective is to find temperature as a function of x. Here. Now this equation is a differential equation of, what do we call it? Degree 2 or order 2? Order 2. Okay. This is an equation of order 2, and if this is an equation of order 2 and we want to solve this problem, so what we need boundary conditions. Yeah, we need boundary conditions. Without boundary condition, we cannot solve the problem. And since it's of order 2, so we need 2 boundary conditions. Okay. So suppose we have a wall. This is our plane wall, and we have a Dirichlet type boundary condition. What was the Dirichlet type boundary condition? The first type, if we have temperature known. Constant temperature, known constant temperature. So suppose the 2 boundary conditions that we have is that we know 2 temperatures. So suppose on this wall we know the temperature at this surface. So suppose this surface is surface 1, this surface is surface 2. So we know temperature Ts1, and suppose we know temperature Ts2. Okay? So our objective is to find temperature at any point in between, temperature variation. Okay, but we know the boundary surfaces temperature, Ts1 and Ts2. Okay, so how do we solve the problem? Okay, K is equals to d squared T by dx squared equals to 0. Okay, into d squared T by dx squared equals to 0. So I can say that d squared T upon dx squared equals to 0. Right? Okay. So what I'm going to do to solve this equation? What do you think? Integrate. This is a differential equation. You have to integrate, right? So if I integrate it, what will happen? So this will become what? dt by dx equals to?
0. No. 1. X.
If there was a constant here, then it will become x. Hmm? Constant. You remember? Differentiation, integration. If you differentiate this term, then it will become d squared T by dx squared equals to 0. Right? But when you have this thing and if you integrate, there will be a constant coming. Ah, calculus 2, huh? This is not differential equation, this is calculus. Okay. So we have this thing. Let's call this C1. Call this C1, and now we can differentiate it further again. Integrate it further again, because we need to find T. So if we integrate it again, then it will become what? T is equals to C1.
C1 square over
C1. C1x. C1 is a constant. C1x plus C2. Are you getting it or not?
Yeah.
This is integration, and this is not even difficult one. This is just very simple one. Okay, this whole chapter is like this. No numerical. All big proofs, derivations, differential. Okay, is it clear? So you got temperature as a function of x, but still there are two constants here which are unknown, C1 and C2. Okay, we need to find C1 and C2. In order to find C1 and C2, we need to use the boundary conditions. Okay, so what are the boundary conditions? The first boundary condition is that suppose this is your x. Your x starts from here. So it's at x0, when x is equals to 0, your temperature is equals to Ts1. Okay, temperature equals to Ts1, right? So let's substitute it. So Ts1 is equals to, when x is 0, that means this term goes 0, equals to C2. So you got the value of C2, okay, because Ts1 and Ts2 are the boundary conditions, they are known. Okay, now let's talk, let's apply the second boundary condition. When x is equals to L, let's say this length is L. Okay, when x is equals to L, T is equals to Ts2. Okay, so once you substitute it again, then it will be Ts2 is equals to C1L plus C2, right? But I can substitute the value of C2. Okay, so if I substitute the value of C2, so this will become Ts1. So that means, can I find C1 here? So C1 here will be what? Ts2 minus Ts1 divided by L, right? So this is my C1. So now I have C1 and C2, I can substitute it here. So C2 here, C1 here, right? I can substitute it. So if I substitute it, it will become what? So T will become C1x. So C1 is this. So I'll write here Ts2 minus Ts1 over L multiplied by x, right? Or let me write it here, Ts2 minus Ts1 multiplied by x by L. Let's write it like this. Plus C2, C2 is Ts1. Okay. So now I got the temperature profile.
The point or the whole?
For whole. So all these are the constant, Ts2, Ts1, L, Ts1. This x is variable. So you change the value of x, you will find the temperature. So when the x is 0, this term will go 0. So T is equals to Ts1. When the x is equals to L, L over L will cancel. Then Ts1 and Ts1 here will cancel. So it's Ts2. Make sense? So you change the value of x, you find the temperature. So that's the temperature profile. Okay. Now if you know the temperature profile, you can use Fourier's law and find out the heat transfer. So Fourier law says what? Fourier law says Q is equals to negative Ka dt by dx, right? So you have T, you have dt by dx. dt by dx is what? dt by dx is C1. Okay, and C1 is what? Ts2 minus Ts1 upon L. Okay, so I can substitute here. So negative Ka dt by dx is Ts2 minus Ts1 upon L, right? Is there an integration here? No, I integrated it to find T, but dx by dt by dx is C1, and C1 is this thing.
So when we have heat, then
Then? What then?
this equation, the first equation, can't change.
When you have heat means?
This one, last one. Q minus equal minus Ka dt dx.
We are finding the heat.
So not connected with the first one equation.
No. Oh, you're saying that, no, this Q is different from this.
Yeah, I know, but we can't change it to.
No, that is different. This is the internal heat generation. What I'm saying is that there is no internal heat generation in our case. I just want to know how much is the heat transfer through this wall.
There is convection with convection because the temperature from T's surface.
Yeah, there will be conduction. Right now, this equation is developed only for the conduction inside conduction. Okay. Right now, we have just considered the wall inside. Okay. We have not considered anything else. Okay. But anyways, first of all, do you understand this? This is a very simple and very beginning small proof derivation type of thing, where we used it for a plane wall with no internal heat generation, one-dimensional steady state heat conduction. And we come up with this temperature distribution, and based on this temperature distribution, this is the heat transfer.
Always ask about the temperature distribution.
Yes.
This is the
Yeah. So questions will become more. Look, the procedure itself is very important, because from now onward, procedure is not going to change. It's just the complexity of the problem will change because of the boundary conditions and other things. Okay, but the procedure would remain same. You start with the heat diffusion equation, eliminate some terms, then first integrate, second integrate. This is this is journal procedure. For the whole chapter, it will be this procedure which will be followed. Okay, and after you have done your first integration, second integration, you will have two constants. You need to apply two boundary conditions to find out those constants. In the end, you are going to come up with a temperature distribution.
so what gonna be the difference between the plane walls and the other?
You'll see.
You will see.
Yeah.
More than two boundaries.
No, two boundary conditions. But we have you'll see. We have a lot of things here left. Okay. So you see here, this is the written. This is written. It's written directly. Okay, these steps were not shown here like that. But anyways, I did it myself by hand as well here. This is my handwritten work, exactly the same thing which I have written on here on board. Okay, so you have first integrates and second integrate, you get this equation, apply the boundary conditions, you will get the value of C2 and C1, substitute the values, and you get this. What happened to the K? Either you eliminate K from the beginning. Why? Because this thing equals to 0. Or if you keep K here, it will become C, a constant will come C. Okay, say that C upon K is equals to C1. It doesn't matter, because K is also a constant. Okay. So this is steady state one-dimensional heat diffusion equation with no internal heat generation. Okay.
The question we use this equation, the last equation, or we need to prove about any state of the equation?
Most of the time you have to prove. Okay. Is there anything within this that you don't understand? Okay.
No number, right?
Yes. There will be some numbers, but after a long derivation. After a long derivation, it will be like, okay, now you have derived this formula. If TS1 is this, at x, yeah, substitute. It's like that. So, but the main question would be for derivation thing. Okay, thermal resistance, we already studied that, right? In the last chapter, I think. Thermal resistance. Okay, and what do you remember what was the thermal resistance for conductor? So R conduction was equals to L upon Ka. And do you remember how does this came?
From
The
the thermal energy, thermal balance.
You remember we say that we have Q is equals to delta T upon R. Then for the conduction we have Q equals to Ka delta T upon delta X. And then we say that, so that means equals to delta T upon delta X upon Ka. And then this delta X upon K, delta X is basically the L. So we have R conduction. Okay, and then you remember what we have R convection? 1 over HA. And what you remember what we had R radiation? 1 upon HRA, exactly. Okay. So now these are the thermal resistances, and we actually we studied them. But in the heat transfer systems, it is very similar to the electrical systems. We can have the series and parallel circuits. Okay. So what do you think? In the series circuit, what is the thing that remain constant in the electrical systems? In series circuit, what is the thing that remain constant in the current? In the series circuit, current remains constant. Current is the thing that flows. In heat system, what is the thing that flow? Heat. So if it is a series circuit, heat will remain constant, like current remains constant. Okay. So in case of parallel circuit, what is the thing that remain constant? Voltage. And voltage is the difference, potential difference, based on which here in the heat circuit you have the temperature difference. So if you have a parallel circuit, then the temperature difference will be constant. Clear? Same analogy, no difference. And similarly, in case if you have the series circuit, then what happened to the resistances? How do you make equivalent? You just add them, right? But if you have parallel circuit, what do you do? Yeah, so you take 1 upon that, 1 upon one resistance plus 1 upon other resistance, then the whole inverse. Okay, remember that? In the electrical circuit. So it's in the same way we will have in the heat transfer circuits as well. Okay.
That means the temperature at the one point is equal to the temperature at the same point that it's current?
Yeah. Suppose I have this is the surface, or suppose this is a surface, and it is rejecting heat as radiation as well as convection. So for the case of radiation and convection heat loss, the temperature of the surface is same. For the convective resistance, this is the same temperature. For radiative resistance, this is the same temperature. So it's so always convection and radiation acts as parallel. Because one end is the same temperature. Okay. So and then normally if you have one wall, other than over that you have another wall, then you have 3 walls, and so if you have this kind of resistance, then they are in series. So conduction resistance mostly are in series. Okay. Yeah. Now let's come over to it. Suppose you have a plane wall here. Suppose you have a plane wall here, and you have one fluid flowing in this direction. You have another fluid flowing in this direction. Okay. And suppose this is a hot fluid with a temperature T infinity 1. Okay. And this is a cold fluid with temperature T infinity 2. Infinity means mean stream temperature. So if when any gas is flowing, if you put a thermometer, whatever the temperature of that, it will be the mean temperature of the fluid. So T infinity 1, T infinity 2. This is a hot fluid, this is a cold fluid. Obviously, you will have a temperature at the surface of this plane wall, and let's call it TS1, and you'll have a temperature at this surface, you'll have TS2. So what will happen actually? So this is the hot fluid, this is a cold fluid. Heat will transfer from hot to the cold. So first heat will transfer from the fluid to the to the surface S1, and this heat transfer will be by convection. Then you will have heat transfer from surface S1 to S2, and this will be by conduction. That one was by convection. Then you have transfer from TS2 to T infinity 2, and this will be again by convection. Okay. So basically in this case you have 3 resistances: convective resistance, conductive resistance, then convective resistance, and all are in series, right? In this case, heat is transferred from hot fluid to the cold fluid, and while passing from hot fluid to the cold fluid, it passed through 3 different resistances: convective resistance, conductive resistance, then convective resistance. So if I draw the circuit here, so the circuit will be one resistance which was convective, then you have another resistance which is conductive, then after that you have another resistance which is again convective. Okay, so here we have T infinity 1, here we have T infinity 2, here we have TS1, here we have TS2, right? So this is the series circuit that we are going to have. Okay. Now, in case if we want to know how much is the heat transfer from start point to the end point, okay, like the voltage difference from start to end, we'll just consider the temperature difference from start to the end, T infinity 1 to T infinity 2. So our heat transfer, Q will be constant here. This is a series circuit. Q will be constant here, right? So our heat transfer will be what? Q is equals to delta T upon R, right? Okay. So if we are considering the delta T from start to the end, so our delta T will be what? T infinity 1 minus T infinity 2. Because T infinity 1 is the hot fluid, high value. T infinity 2 is the cold fluid, lowest value. Over R total, right? Okay. Now what will be the R total? We have to add the 3 resistances, right? So what's the resistance of convection? It's 1 upon HA, right? But HA for the hot side. Okay. Then conductive resistance, what is this? L upon Ka. Okay. Then convective resistance, what will be? 1 upon HA, but for the cold side, right? So if you add these 3 together, this plus this plus this, that will be the total resistance. Substitute the value here, and you will get the heat transfer. Is clear?
Yeah.
The same analogy as you studied in electrical systems. You have a series circuit, add the resistances.
The direction doesn't matter.
Yeah.
Direction, I mean the direction of the, in your figure, direction, up or down, or
No, the fluid direction.
Yes.
It doesn't matter. It just means to say that there is a hot fluid here, there is a cold fluid here. Is it clear? This direction will matter in chapter number 11.
Because here the control is up.
Yeah, here it does not matter. The important thing was to understand this thing.
So this is the wall. Have to the 2 sides have fluids. That's the concept.
That's the concept. Now you have to understand one thing. The resistance is always considered for the in between the 2 points where temperature is being taken. Right? Resistance is always considered between the 2 points where voltage is considered, where potential difference is taken into account, right? So here I took T infinity 1 to T infinity 2. So R total is this plus this plus this. Now you tell me one thing. If I say instead of T infinity 1 to T infinity 2, I say here T S1 to T infinity 2.
So
Yes, perfect. If I say T infinity 1 to TS2.
So what the cold side is the resistance of the cold side
Then now we are not considering that. The R total will have only. Okay, khalas, if you understand this, that's it. You understand the concept here. Okay, let's move ahead.
It will be T inverted minus TS2. This one above. T inverted minus TS2.
Each question, if I done like this, I should consider the start point and the end point. So, then communicate with the other points in the series.
Yeah. So look, it depends. Suppose if you are not considered about the temperature Ts1 and Ts2, you don't need it. Khalas, then solve it from start to the end. Suppose you have cold water fluid temperature, but you do not have Ts1, then you can consider only this region. So cold fluid temperature you already have, you can find Ts1. It depends what is the thing you need and what procedure you have to follow to find. Okay.
One question. So you can combine between this and the before question, right?
I can combine many things, but there are many other things left. I don't need to do. If I want to play, I can play in many ways, but I don't need to play, because even if I keep simple, there are so many things that you will face. Okay, anyways, now consider this one. It's same problem, but instead of having one wall, now you have 3 walls together. And this actually happened. For example, even if you consider the walls which are made here, it's not just a single wall. I mean, you have the brick, above the brick you have the plaster. Plaster is a different material, it will have a different K value, it has different thickness. Above this you have the paint. Paint has different thickness, paint has different K value. So you have paint, plaster, then the brick, then after that again plaster, then paint. So within this wall it is composed of 5-6 components. So this is the thing, normal occurrence. This is how it happens. Okay. So so suppose if we have a wall, a composite wall. This is known as composite wall, mushakkal. Okay. So it's a composite wall, 1, 2, 3 of different components. Okay. And the thing that vary means, whenever we say composite wall, it means that the material of the wall is changed. Okay. So obviously material of the wall will change, so that means K will change. If K will change, thermal resistance will change, because it depends upon L upon Ka. Okay. So anyway, suppose you have 3 walls here together, A, B and C. The length here is LA, here length is LB, here length is LC, and then you have a hot fluid here and a cold fluid here. Okay. So now how many resistances you will have? First of all resistances are there in series, because we are not considering radiation right now. Okay. Normally radiation and convection goes parallel. So, but here right now radiation we are not considering. So all resistances in series. So first we have the convective resistance, then conductive, again conductive, again conductive, then convective. So 5 resistances in series. Okay. So T infinity 1, then we have, let's say, Ts1, T2, T3, Ts4, T infinity 4. Okay. And all will have the heat flow will be constant, because this is series. So it will be Q. Okay. And the resistance for the first convective one will be 1 upon H1A, then L upon Ka for A, L upon Kb for B, L upon Kc for C, then 1 upon Ha for cold side. Okay. So if we know T infinity 1 and T infinity 4, then we can find, we will use the resistances all together. So it will be sum up of all together. So you see here. Okay, now there is one thing, when you have multiple resistances, convective, conductive, radiative, okay, the more easy thing is that we write equation in the format like this. This format, you know, convective format, Q is equals to HA delta T, right? This is the most easiest format. Okay. So, but if you have not just convection, if you have also conduction here, if you also have radiation and a combination of multiple things, so we call it overall resistance. Okay. So overall heat transfer coefficient. So it's not just now convective, it's overall heat transfer coefficient. So we give it another name. Instead of calling it H, we call it U. U means overall heat transfer coefficient. H was convective heat transfer coefficient, but U is overall heat transfer coefficient. Okay. Because U could be composed of convection, convective resistance, could be composed of conductive, multiple conductives in series and parallel, radiative, overall. Okay. So you know that actually Q is equals to delta T upon R. This thing you know. So what's the relationship between UA and R? UA is equals to 1 upon R, right? So UA is equals to 1 upon R, or you can say U is equals to 1 upon RA, right? So since this U is for total, so it will be R total, right? So this will be R total, R total. Is it clear? In this case, R total will be what? If you add all together, right? So if I add all together, so that will be R total. But U is equals to 1 upon R total into A. So you have to, once you have R total, you have to multiply it with A as well. So if you multiply R total with A will cancel, 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 right? So U upon 1 upon RA total is equals to 1 upon H1 plus L upon K plus L upon K plus L upon K plus 1 upon H2. Is it clear?
Yeah, so now we found the coefficient. Generation. So we can use that.
Do you understand the coefficient? Do you understand the concept here?
I can solve it without U.
Actually, U is needed most of the time. Why? Because industrially the materials which are provided, they give the U value for the material. Because when you give the U value, now you don't consider whether that it is because of convection, conduction, whatever. Then they say, okay, we are the manufacturer of the material, we have determined it. This is the U value. They make things simple for the ones who have to use them. The user don't know the theory behind. Okay, so that's why for you knowing U is important. Is it clear so far? This is the same thing. I've just done it myself with hand. Okay, you see, I cancelled A with this A because I say it's R total into A. Okay, and just made the same relation which I put here. What's the relation between UA and R total? That's it. The heat is about to begin. The heat is about to begin. Summer is about to start. Yes. Okay. So if we have now this is a special case. This is a special case. Suppose you have a composite wall like this. So you have one wall here, then you have another wall, third wall, fourth wall, and you have a temperature T1 here and temperature T2 here. Now suppose heat has to flow from T1 to T2. Now how would you draw the circuit? The heat circuit here, it will be a bit complicated because there is a possibility that the heat transfer will occur from the wall E to the wall F and the wall E to the wall G, but might be there will be a heat transfer between F and G as well. Then it does not remain one-dimensional flow, then it's a two-dimensional heat transfer. Then there will be heat transfer between G and H and F and H, right? So anyways, we can still solve it using one-dimensional, but if we have to solve it using one-dimensional case, we have to make an assumption. Now there are two possible assumptions that you can make. Okay. The first assumption is that if you assume, for case A, if you assume that the surfaces normal to the x direction are isothermal, this is your x direction. Okay. So what you say is that surface normal to the x direction, that means parallel vertical surfaces. All vertical surfaces are isothermal. If you consider that all vertical surfaces are isothermal, then in that case your circuit would look like this. Because vertical surfaces are isothermal means this surface, this edge of E, okay, this edge will have the same temperature, and then these two will become parallel to this. Because this edge has the same temperature, this edge hole has the same temperature, between these two edges you have these two. So they become parallel, right? If you assume that all vertical surfaces have uniform temperature. But if there is a possibility that you think that no, it's not possible that all vertical surfaces have the same temperature, might be the temperature at the top side is a little different than the temperature at the bottom side, then you cannot solve it as a single one-dimensional problem, because then there is a possibility that the heat flow up and down as well. Then you make another assumption. You say, okay, surfaces parallel to x direction are adiabatic. That means you are saying that yes, there is temperature difference between top and bottom, but heat will not flow from top to bottom, because all the x surfaces, all the horizontal surfaces are adiabatic. Adiabatic means they will not allow heat to transfer from top to bottom. I mean, this is an assumption. An assumption means there will be some error in your solution, but sometimes the error is acceptable. Okay. Yeah. So suppose if really the temperature difference between top and bottom is not that much, then the heat transfer, the transverse heat transfer, the heat transfer from top to bottom will be little. Even if you ignore it, your answer would be a little wrong, but not that much. Okay. So if you assume that all the horizontal surfaces are adiabatic, then you will have two circuits like this. If you assume that all the surfaces are adiabatic, because this surface, this complete surface is T1, this complete surface is T2. Okay? But then all surfaces are adiabatic, horizontal ones. So you will have one separate circuit following this line, one separate circuit following this line. Okay? But if you assume that all the vertical surfaces are isothermal, then you will have one complete surface here, same temperature, one complete surface same here at that same temperature, and then you will have resistances in between which are parallel. So there are two ways of solving this problem. Either you can consider this circuit, or you can consider this circuit.
We do this assumption with the second dimension test.
We just why are we doing these assumptions?
To make it one-dimensional.
To make it one-dimensional. Okay. Otherwise, it's not a one-dimensional problem. It becomes a two-dimensional problem. Anyways, we are not solving this problem, but it can come in the short questions in the sense that, okay, draw the circuit and the two possibilities. So you have to write these sentences. Yeah, you have to write these two cases and draw these two circuits. Or maybe I provide you one of the case statement and say draw the circuit for it. Okay?
So no star?
It's a star. What's the contact resistance? Look, we discussed the mushakkal, we discussed the composite wall. Okay, so what happened is that many times the walls, even if they look smooth, they are not smooth. If you see on the microscopic level, the wall is something like this. Okay, so it's a little like this. So if when the two walls are in contact, when it becomes a composite, so if you make another wall in contact, still you will have some pockets of air in between. These pockets of air offer a huge amount of resistance. Okay, because you know, for conduction, air is a very poor conductor. Metal is very good. Okay, solids are better conductor. Liquid are not as good as solids, and air is the poorest conductor. Okay, so this offers a huge amount of resistance to heat flow, because we are talking about the heat flow by conduction. Okay, so we have the contact resistance here. So sometimes what we do is that there is some filler material. It's a liquid material, but it fills in the place, in the space. Okay, so the filler material also has some resistance, but at least its resistance is very, very small compared to that of the air. Okay, so so now not just, okay, we have a conductive resistance here. Suppose we have one material A here, one material B here. So we have a conductive resistance here, then you have another conductive resistance here, but in between where you have the contact occurring, you also have another resistance here, and which is the contact resistance. Contact resistance. Because the two walls are in contact, and in between there could be air, maybe there you put a filler material. And so there is a table in your book, table 3.2, and which is actually also added in the book of tables, book of formulas, and which have that what kind of a filler material you are putting. Is it an epoxy or what kind of filler material, and what is the resistance of that material? So directly the resistance is provided. So in case you are required to use it, you might have to use it. Okay, depends upon the question. It's very better than air, but still it has some resistance.
This is this space is rejecting heat.
No, look, the thing is that I have one material, A. I have another material, B. Now, the heat need to be transferred from this surface. Let's say this surface is 1, this surface is 2, this surface is 3. So there will be conductive resistance here between A to B. Okay, then there will be conductive resistance here, or you can say there is conductive resistance from S1 to S2, then there is conductive resistance from S2 to S3, right? But we neglect one thing, that in between there could be air pockets. And this is also providing another resistance here. So now it's not just two resistances. There are three resistances in series now. Okay, so one resistance, and then another resistance, then third resistance. Okay, now this resistance, what is this resistance? Depends upon, maybe you put a filler material in between in order to remove the air, and so the resistance is reduced, but it has some resistance.
Yeah, but
Very less, but still.
It's like the double glass. They put a small gap for air, so it will detect more heat. You touch the glass from the side, there is no.
When you have double glass, you don't put air in between. Do we put air in between?
No, I mean the big glass for balconies and windows. There is a gap between the two glasses. I read about it and fight for the heat detection.
Yeah. So what we do is that if you have two glasses, even if you put a small amount of air in between, so now the resistance of one glass plus resistance of the air plus resistance of the third glass, of the second glass, but the resistance of the air is very high. So your heat transfer reduces a lot. When you increase the resistance, heat transfer will reduce.
this is the benefit.
This is a benefit, okay? But this is a benefit when you want to stop heat transfer.
Yes,
But if you want heat transfer, this is a big disadvantage. Okay?
When we have walls like this, like A and B, and we have some gaps between them, it will be like there is another two surfaces, like A, that side and B, A and B.
Yes. So now it will not be S2,
Be S3 and S4.
4, yes. But what we do is that normally what's done is that since S2, so it's like now S1, S2, S3 and S4. Okay, so but S2 and S3, they are so close to each other and they directly provide you the resistance for this. Okay, so you can consider them one, it's okay, because you have the resistance. Okay. Is it clear? Shall I move?
yeah.
Okay, contact resistance. Okay. So let's have an example here. Yeah, this one is with numbers. Okay. Okay. In example 1.7, they want us to move back to chapter 1.
Just scale of 2.2.
Hmm?
Fluid, non-fluid. This is what you have.
Okay. Yes. Do you remember a problem where we discussed human body? It has a skin, fat layer, okay, and how much heat transfer from the skin.
57.
So it's the same problem, but now they say that over the skin, a person is wearing a snow suit. What they call it? Snow suit or wet suit. This snow suit is a special suit, is a special cloth, which will reduce the heat transfer. We will reduce the heat transfer because the person is in water and a huge amount of heat will be lost from it. You don't want a lot of heat to be lost from the person. You want the body temperature to be maintained. Okay, so now he's wearing another suit, but we need to, as engineers, we need to determine what should be the thickness of that suit. How thick should be this suit? Okay. So if you say 2 millimeter, then you're wrong actually, because when the solution is done, you'll find it's about 4 point some millimeter. Okay, in example 1.7, we calculated the heat loss rate from a human body in air and water environments. This is what we did, heat loss from the body. Now we consider the same conditions, except that the surrounding air or water are at 10 degrees centigrade. So now the air or water surrounding is at 10 degrees centigrade. To reduce the heat loss rate, the person wears a special sporting gear, which is a snow suit or a wet suit. So he wants to reduce the heat loss from the body, so he's wearing a wet suit or snow suit, they call it, made from the nano-structured silica aerogel insulation. This is the material of that suit. With an extremely low thermal conductivity. So the thermal conductivity of this suit is very low. It's 0.014 watt per meter Kelvin. The emissivity of the outer surface of the snow and wet suit is 0.95. Okay, so that's the radiation heat transfer. What thickness of aerogel insulation is needed to reduce the heat loss rate to 100 watt? A typical metabolic heat generation rate in air and water. What are the resulting skin temperatures? So the thing is that normally the metabolism which is occurring, as I told you, there is a thermoregulation within human body. So human body is continuously generating heat. Okay, so normal metabolism of a human body is that it is generating about 100 watt of energy. So a person normally is making 100 watts of energy. We don't want more energy to be lost from the body. We want the energy loss will be there, but we want to restrict it to 100 watt. Okay, it should not be more than 100 watt. And in this way you will not feel cold, because the amount of heat generated is now going out. So not more amount of heat is taking out, just the amount of heat which is being generated is going out. Your body temperature remains constant. Okay, so you want to reduce the heat loss rate to 100 watt. Now we need to decide what should be the thickness of the wet suit so that it reduces the heat transfer rate to that much. Now let's try to remember how the problem was before. Okay, last time when we were solving, it was like that. You had the skin fat layer, if you remember, that was the skin fat layer, and I think if you remember it was 3 millimeter. Yeah? The surface south, 3 millimeter.
Why are you so blind?
Huh? No, because the person height is high, it's 1.8 meters. 1.8 meters square was the overall area. So yeah, but 1.8 meters is high. It would be south, it cannot be blind. Okay, so we had the skin fat layer, and you remember inside of this layer the temperature was 35 degree. Body temperature was supposed to be 37. Below the skin layer temperature was 35 degree. Now what they are saying is that above this skin fat layer you have another layer, and that is of the wet suit, okay, and but the thickness here of this is not known. L. They want you to determine the thickness, okay, and above it, last time there was heat transfer from the skin fat both by convection and radiation. Now again it will be by convection radiation, but not from the skin but from the wet suit out. Okay. So if we draw the circuit, if we draw the thermal circuit, so you have a conductive resistance here in the skin fat area, then you will have another conductive resistance between the wet suit, but after that you will have a convective resistance and radiative, and they should be parallel because they are coming from the same temperature surface. Okay, so okay, it's like this. It's clear? And now this temperature is known. This is what do they call it here? Ti. Okay, they call it here Ti. Okay, T inner, and this is Ts, which is not known, skin. Okay, and what do they call this? Let me see. They did not say it anything. Anyways, you have then this is your T surrounding. Okay, for and this will be T infinity. Okay, this will be for convection. The convective resistance, it will be 1 upon HA. It will be 1 upon HRA. Right? Okay, and this should be L upon Ka, and this should be L upon Ka. Right? And one thing that we know is that the heat flow should be limited to 100 watt. Okay, we know that the heat flow should be limited to 100 watt. Okay, so now if we want to solve this problem, since in this case T infinity and T surrounding are same, T infinity and T surrounding are same, and it is 10 degrees centigrade, 10 degrees centigrade. Okay. So now what temperatures we know? We know these two temperatures, the very inner and the very outer, but we don't know the in-between temperatures. So let's leave the in-between ones. We use the ones for which we know the temperature. Okay, so let's do it like this. Q is equals to delta T upon R total. Okay, Q is known. Okay, delta T, let's take delta T from inner to outer because we know. So it's T I minus T infinity or T surrounding. Okay, and R total. Okay, R total will be what? Okay, so let's call this skin fat. So let's call it LF, KF. This wet suit LS, KS. Right? Okay, so it will be LF over KFA plus LS over KSA. Then so then I will say 1 upon. Okay, so if it is like this, then we do it like if this is the resistance, right, and this is the resistance, or radiation, sorry, radiative, or convective. Okay, so we say that R radiative plus R convective, if yeah, R radiative plus R convective is like this, right? Is it like this? Or is it 1 over? I think 1 over. 1 over R plus 1 over R. Now, right? Right? So, 1 upon R radiative will be what? 1 upon R radiative will be HRA. Right? So, let me directly write here. Directly HRA. And this will be HA. Okay? Okay? So now we know the area because it's the same problem, same person, same south. So we have 1.8 meter square. Okay, so we know the areas. We know this H, and HR was what? H was epsilon sigma TS plus TS plus T surrounding. So
This is
Multiply
square.
by the square. Yes, square plus T surrounding.
yeah, plus TS square plus T surrounding square. Okay, so net. Let me. Okay, now in this equation, everything is known
Except the LS.
except LS,
Yeah, so which is
which was required.
yeah.
Because you know Q, you know delta T, you know in the resistance only LS is unknown. Okay, so the only thing that we need to do is you need to substitute the values and you'll find length for the insulation, and length for the insulation comes out to be 4.4 millimeter. In case of if it was in air, if it was in water, then you will not have radiative resistance. Okay, just the convection. Okay, and then everything is like in series. Okay, and in that case, if this is the case, and when you solve it, you will find that the insulation required is 6.1 millimeter. Okay, so in case of air, insulation required is 4.4. In case of water, insulation required is 6.1 millimeter. And that makes sense because in water you will feel more cold. Your water, the heat will go up. Yeah, yeah. So it's like this. And what next? What was asked? Okay, need to reduce the heat loss. What are the resulting skin temperatures? Okay, so skin temperature is here, TS, right? Skin temperature is here. Now, if I want to know the TS, then I can use this one because Q is the same. I can use this from TI to TS. Okay, so if I use this one only, Q is equals to TI minus TS, or here R will be what? LF upon KA. So you know Q, you know TI, you know LF, KA, you know what will be TS. And they also did it like this, yes. So that's it.
Just asking how can I know there is resistance?
How
I know that.
Well, in chapter 1 there is no resistance. So we ask what.
how do we know there is?
I use the resistance method, or I use the chapter 1.
Actually, even chapter 1 method was also resistance method. Just we did not draw the circuit. Only the thing was that we did not draw the circuit. Here only the new thing is that I'm not drawing the circuit. Otherwise, it was the same method. Okay. When we are using this, okay, remember, I remember what we did there was that we said Q conduction is equals to Q convection plus Q radiation.
Yeah, that's why
It's the same thing. Either you use this method or this method, both are same. Okay. Yeah, but sometime you will get a hint because in the question, if one of the part is draw the heat circuit, then you know the direction. Huh? Yeah. Sorry?
Schematic like this in the exam.
A schematic will be provided to you, but not with the heat circuit. Okay, so like this will be provided to you, but this will not be there. You have to draw this thing yourself. Okay?
The numbers.
Yeah, with the numbers. This picture will be there as it is.
Doctor, why the last example before that the one that before we do there is no
there was no emissivity given in the problem, okay, and it was assumed that the radiation effect is not significant. Okay. Normally when it is there, then the things related to it will be provided to you. And the most important thing in case of radiation is the emissivity. You have not provided a,
If it gives me the emissivity,
yes,
I will consider the radiation.
then you consider the radiation component as well. Okay.
Is that the question?
Okay. Do you understand the problem solution or not? Okay. Okay. Now this is a problem. We have a thin silicon chip. Now, in heat and mass transfer, if you have a numerical problem, each and every word counts a lot. It means something. Okay. So when they have written a thin silicon chip, thin has a very significant meaning. The meaning of thin is that it is really very thin, it has no thickness. Okay? It has thickness, but it's negligible for this problem. So that's why in the heat and mass transfer, most of the time the questions, when you have a question statement, it's very important, each and every word is very important because it means something. It will affect your solution procedure. Okay? So here in this case, it begins with a thin silicon chip. That means the thickness of the chip will not be provided to you. That means it's irrelevant. It's not providing any resistance, or the resistance provided by it is negligible for the question point of view. Okay? So we have a thin silicon chip and an 8 millimeter aluminum substrate. What's the substrate? Substrate is, you know what is a substrate? Substrate is sometimes if you have very thin chip, it's very hard to hold the thin chip. So you make a base and put the chip on it. Then you move the base so the chip moves, or wherever you want to place it. You don't directly hold the chip in hand. You put it on a base. Okay. So substrate is a base. But what we do is that we just don't simply put it. We actually emboss it so that it does not move away from the base. We fix it like computer chips. So normally even if you see the computer circuits, or if you see the solar panel there when we went to the CACs, okay, so even the solar panel silicon chip was put on a substrate. It was a green color film which was a green color plate on which everything was placed. So that's a substrate. Yeah, it's like a base. Substrate is a base. Okay, a thin silicon chip and an 8 millimeter thick aluminum substrate are separated by a 0.02 millimeter thick epoxy joint. So the thing is that you have a chip very thin, so I will not draw its thickness. It's very thin. And then you have a substrate which is 8 millimeter thick. Okay. And as I told you, when the chip is placed on the substrate, it's not just simply placed; it is embossed. Okay, so it's joined by now. So for joining, they put an epoxy joint. Epoxy is a paint, so it's like they put a paint and then they put the chip on it. Okay, so it's the paint thickness is how much? 0.02 millimeter thick. So 0.02 millimeter thick. 0.02 millimeter thick epoxy joint in between. Okay, so you have the chip, you have the substrate, you have the epoxy joint. Okay, the chip and substrate are each 10 millimeter on a side. So this, if you see it from the top, so it's square with 10 millimeter on each side. Okay, and their exposed surfaces are cooled by air, which is at a temperature of 25 degrees centigrade and provides a convection coefficient of 100 watt per meter square Kelvin. If the chip dissipates 10 power 4 watt per meter square under normal conditions, will it operate below a maximum allowable temperature 85 degrees centigrade? Now you see here, it's not written, but the diagram which is drawn here, which will be provided to you, it shows there is insulation on the two sides. See, these are dotted. This is insulation. Okay, so it means you have a chip. Suppose this is a square chip. Okay, suppose you have a square chip, and so chip is there on the substrate. Okay, but at the all sides you have insulation. Okay, so you have air at 25 degrees centigrade blowing over it and below it. Okay, so the heat loss can be done from the top, heat loss can be done from the bottom, but cannot be done from the sides because sides are insulated. Hmm? Yeah. Hmm? So you have up and down, two sides where the heat loss can be done. Okay, so if you see here, suppose this is your chip. Okay, suppose this is your chip. Okay, so on the above side, okay, tell me, is there any emissivity provided?
No radiation.
That means we assume that there is no radiation effect. Emissivity is not provided. Okay, so from the top, what kind of loss is possible? What kind of resistance will be there? Not conduction. It's only convection. You have the chip. Chip has no thickness. Neglect the thickness. So above the chip, you have just the air. So just convection, right? So above the chip, you will have convective resistance. Okay. Now below the chip, because there are two ways the heat can be lost, going up or going down. Okay, because this chip is dissipating energy. This much amount of energy is being dissipated by the chip. Okay, so this energy, when dissipated, when taken out from the chip, will be lost. But how will it go? It will go up and down. Okay, now from up, when it goes up, so only one resistance, convective resistance. But when it goes down, it will first pass through the epoxy joint, then pass through the substrate. Okay, so first energy will go below the epoxy joint, then pass through the substrate, then go out. Right? So how many resistances? Below? Three. Right? One for the substrate, one for the epoxy joint, one for the substrate, one for the convective. Okay, so this is, let's say, call it this TC chip. Okay, then we have the epoxy resistance, TE or resistance of the epoxy. Then we have substrate, epoxy. Okay. Then after that, convection. Okay. Now this was the chip and the substrate, and air is blowing over and below, right? So it's the same air. So the air temperature was 25 degree, right? So above temperature is also T infinity 25. Below temperature is also T infinity 25, because it's the same air which is blowing from the top and from the bottom, right? So it's like that. Now it's written that the convection coefficient is, which provides a convection coefficient of 100 watt per meter square Kelvin. So for the convective resistance, it will be 1 upon HA, right? This will also be 1 upon HA. But this H and this H is given. This is because of the convection coefficient for the air, and it's provided, right? For the substrate, it will be L upon Ka, right? L is the thickness of the substrate is given. 8 millimeter thick aluminum substrate. Okay, and what about K? K is given? K is not given for the substrate. Okay, and for the epoxy joint, again L upon Ka, but L is given because epoxy joint is 0.2 millimeter thick. K is not given, right? And what do we want to know? We want to know, okay, now the question is that if the chip dissipates this much amount of energy, under normal condition, will it operate below a maximum allowable temperature of 85 degree? So the thing is that the allowable temperature for the chip is 85 degrees centigrade. If the temperature becomes higher than 85 degrees centigrade, chip will be damaged. You don't want chip to be damaged, but we don't know whether its temperature will reach 85 or not. Okay, so basically our objective is to find out the chip temperature. This is what we need to find, chip temperature. If chip temperature is higher than 85, that means I will say that it will not.
The same as the T surface?
Yeah, you can consider it T surface. What do they write here? No, they write here TC. It's like T surface, surface of the chip. Okay, and so we need to find this temperature. If this temperature is below 85 degree, we will say yes, it's working under allowable temperature. If it is above 85, say no, it's not working under allowable temperature. But this is what we need to find. Now let's see one thing. This chip is dissipating energy, and this energy dissipation can go up and down. But the total amount of dissipation is this, right? So let's say if the amount of energy going up is Q1 and the amount of energy going down is Q2. We don't know Q1, we don't know Q2, but we know Q1 plus Q2. Okay, so Q is equals to Q1 plus Q2, where Q is 10 multiplied by 10 raised to the power 4. What's the unit? There is a problem. So that means, so that means it's a flux. It's a flux. That means we can say that we know Q double dash, right? So Q double dash is equals to Q1 double dash plus Q2 double dash, right? You can do it like this. Or we can multiply it by area, but in any case, everyone will be multiplied by area. So and areas are same because it's going up and down, same 10 millimeter by 10 millimeter on one side. Okay. So this thing we know. Okay. So what will be Q1 double dash? Q1 double dash is the energy going up, right? So it will be delta T. What will be delta T?
25.
20.
TC
Minus
Do,
No, TC minus.
TC minus 25 because heat is moving from chip to outside. Okay, so it will be TC minus 25 divided by resistance. Okay, and resistance will be what?
L.
1 upon H. I will write here just H.
Because the
No, without A, because it's plus.
Yes. Okay. So because it is flux, right? If I write here HA, this is basically Q, right? So, okay. So when we have to put flux, so that means flux is Q upon A. That means this thing upon A. So here A and A will cancel, right? So I'll write here just 1 upon H. And this H is known, right? What about Q2? Its temperature difference is again the same.
Yeah, the TC minus 25.
TC minus 25, it's again the same.
The resistance is
So we have 3 resistances, right?
yeah.
We have 3 resistances in series.
And then it has
Why 3? Because we have epoxy, substrate, then convection. Okay. Now for the case of epoxy, I don't need to use L upon Ka. Why? Because this is an epoxy joint. It's basically paint, and its resistance value is directly provided in the table. Table 3.2. 0.2 millimeter epoxy resistance. Table 3.2 provide directly the value of resistance.
yeah.
So
So
you see here, Hmm?
The epoxy should be given.
It's given.
So table will be there with you in the book of tables.
So it's given.
We need to see that.
Yeah, table will be given to you and the book of tables. Okay, so this resistance is there, RTC. Okay,
The value
directly value R given. Plus, for substrate, we have L upon Ka, where the value of K, okay, value of K you have to get from the appendix. Because aluminium and K is a thermal conductivity, but it was not given in the question what is K.
So we need
But temperature was given, at which temperature where it's going to operate. So pure aluminium appendix A1, table A1, will give you the K value 239 watt per meter Kelvin. Okay?
how this would be again?
For after epoxy you have the substrate. Substrate is aluminium. For aluminium you have to get the K value from the table.
The aluminum.
For aluminium, K value from the table. It's clear?
temperature, we don't know how to get
It's
the
solid,
temperature.
so solid, but doesn't mean-
It's solid, so even if you take the temperature of whatever given, I think temperature given is 300 or 350 Kelvin, you take the value from that, it's good enough. Okay. So we have L upon K. I'm not writing here A
Because same flux.
because same flux issue. Okay. So we have this L upon K. L is given, K you get it from the table. Then after that 1 upon H, right? So H is known, LK is known, RTC is known. Only in this equation TC is unknown. So you'll get what is the temperature of the chip. Once you get the temperature of the chip, then you see what temperature is coming. So, okay, so once you do solve this problem, you will find out that the temperature coming is 75.3 degrees centigrade. 75.3 degrees centigrade means it's working under the allowable range. Okay. Sorry? RTC is the resistance of the epoxy,
Yeah, it's
which you get directly from the table. Okay.
just like this is the maximum. This is the maximum.
No, this is the maximum temperature at which it is operating. Okay, and it is said that it should operate below 85 degrees centigrade. So that means it is operating under the allowable range. Okay, so hence the chip will operate below its maximum allowable temperature. Maximum allowable temperature is 85. So don't operate above 85 degree.
How is TC 25 plus?
It's after manipulation. You get this thing. This is what is there right here, right?
Okay, yeah.
Okay. Now you know Q, you know H, you know RTC, you know L, you know K, you know H, you know T infinity. Find out TC. Use mathematics. Use calculator. Okay. This is a simple mathematics now problem.
Yeah.
Is okay? This was the problem I gave in the final.
Chapter 3. Allah.
This was the problem I gave in the final, but a modified version. And this is a little complicated problem. Let's go with it.
Just had to give them.
For the last problem, you have anything that you do not understand? The mathematics I'm not solving because it's understandable that you can solve the simple mathematical equations. Okay.
This is the longest. How about this?
Sorry.
It's the longest question.
No. You are just in the beginning. The longest question of is there in chapter 11, yes. In the last question of chapter 11.
You put it in the exam?
No, I did not get. Maybe in your exam.
Oh, yeah.
I can make a separate exam for you.
If they can make for us a small question, like which color your favorite?
Okay.
Why this color make?
Okay, now let's come to this problem. This is a little complicated problem. You have to focus a little in this problem. This problem is much related to, in fact, this problem is going to help you a little in the renewable energy course as well. Okay, and you have seen this. You saw the manufacture of photovoltaic panel in the CAXT when you visited there. Okay. And if you see there, it's not just one layer. There are multiple layers. First, they take the substrate, then they put a soldering layer, then they put the chip, then they put adhesive, then they put the glass. So that small photovoltaic panel is composed of multiple layers. Okay. So let's read the problem. We have a photovoltaic panel. It consists of top to bottom. It's written from top to bottom what are the layers. A 3 millimeter thick ceria doped glass. So that's 3 millimeter. From the top, the first thing is the glass, which is 3 millimeter thick. It's ceria doped glass. Its Kg value, K thermal conductivity value is given. A 0.1 millimeter thick optical grade adhesive. So you have a glass. After that glass, you have the glue, an adhesive, with which the glass is stick. Okay. And for the adhesive, the thermal conductivity value is 145 watt per meter Kelvin. Then a very thin layer of silicon. Silicon is the most important thing which produces electricity. So you have the glass, then adhesive. Below adhesive, you have the silicon layer. Okay. Within which solar energy is converted to electrical energy. A 0.1 millimeter thick solder layer. So after the silicon chip, you have the solder layer. So let me draw it here. So you have first you have the glass, then you have the adhesive, then silicon chip. Silicon, what do they call it? Chip or what? Silicon. Then the silicon. Okay. After silicon, they have solder. Yes, you have the solder layer. Solder layer is the layer through which the electrical circuit is made. The chip is going to generate electricity, but you want electricity out of the panel. How do you get it out of the panel? It's through the solder layer, which proves as a wiring circuit and takes out the electrical energy. Okay, and then after solder layer, you have a 2 millimeter thick aluminum nitride substrate. Then after that, you have a substrate. This substrate is the green color panel, the green color base over which everything was put. Okay, so you have the substrate here. I don't know. Okay. Okay. The solar to electrical conversion efficiency within the silicon layer decreases with increasing silicon temperature. So the thing is that you see here we have the silicon layer, but the efficiency of it, you have solar energy coming. So you have the sun and solar energy is coming from here. But the efficiency of converting solar energy to electrical energy depends upon the temperature of the silicon layer. Okay? So if the temperature rises, the efficiency drop. If the temperature is low, efficiency is good. Okay? So silicon layer efficiency decreases with increasing silicon temperature. So this TSI here, TSI is very important, silicon layer temperature.
So doctor, we can consider the silicon to insulation?
Look,
Not insulation, I mean, just to keep the whole component at the level of the temperature which is used.
the problem is that we need solar energy to fall on the silicon layer. When the solar energy will fall on the silicon layer, it will produce electricity. But whenever solar energy fall over anything, its temperature rises. It's right.
Yes, yes.
So the only way to stop rising the temperature is that you do not allow the solar energy to fall on it. But then you do not get any electricity.
So there is maximum limit.
So there is a compromise here. Okay, then there are different ways. So now you need to limit the temperature. So maybe you can try to extract the temperature, the heat from here.
As the temperature for a different plant.
Yes.
So from calling the solar plant.
Yes. Okay. Okay, and it is described by an expression efficiency is equals to A minus B T silicon. Okay, so the efficiency of the solar or silicon panel or the solar panel is given by the A minus B T silicon. Okay, where A is 0.553. I can put the value here. 0.553. B is 0.001. The temperature T is expressed in kelvins. So this temperature T silicon is in Kelvin over this range. Of the incident solar radiation, G equals to 700 watt per meter square. So the solar radiation which is coming, that is G, it is 700 watt per meter square. Okay, of this incident solar radiation, G equals to 700 watt per meter square, 7% is reflected from the top surface of the glass. So out of this, when it comes here, 7% is reflected. 7% is reflected. Okay, 10% is absorbed at the top surface of the glass. Okay, so let me also put here glasses here. Okay, so the remaining goes into the glass, but out of that 10% is absorbed within the glass. Okay,
Now 83.
now 83. Okay, and 83% is transmitted to and absorbed within the silicon layer. So the remaining 83% passes through the adhesive, goes into the silicon layer. Okay. Part of the solar radiation absorbed in the silicon is converted to thermal energy. Now, the thing is that when this 83% fall on the silicon layer, not all of that 83% is converted into electricity. So there is an efficiency. Okay, there is an efficiency based upon the temperature of the solar or silicon chip. So obviously the efficiency is less than 100%. So part of it is converted into electrical energy. What happened to the other part? The other part raised the temperature of the silicon chip. So it will be converted into heat. Okay. Part of the radiation absorbed in the silicon is converted to thermal energy, and the remainder is converted to electrical energy. So this 83% part is converted into thermal, part it is converted into electrical. The glass has an emissivity of 0.9. Glass has an emissivity of 0.9, so emissivity is given. And the bottom as well as the sides of the panel are insulated. So there is sides as well as bottom, sides and bottom are insulated.
Only the top.
Only the top is the one from where heat can be lost. Okay. Okay. Determine the electric power produced by length 1 meter by width 1 meter solar panel for conditions characterized by H. H is given. So H will be for the convection, and the H is 35 watt per meter square Kelvin. And T infinity and T surrounding are same, which is 20 degrees centigrade. So T infinity equals to T surrounding is equals to 20 degrees centigrade. So first of all, do you understand the problem statement or not? What do we need? We need to find the power output. Okay, power output coming out of the silicon layer. Okay, P output. So you have solar energy which falls on the glass, 7% reflected, 10% absorbed in the glass, 83% goes to the silicon. Silicon has an efficiency, it produces electricity, remaining converts into heat. Heat cannot be rejected from the sides and the bottom, it have to be rejected from the top side. At the top we have the convective heat transfer coefficient of 35 watt per meter square Kelvin. Emissivity of the glass is 0.9, T infinity, T surrounding is 20 degrees centigrade. We need to find out the power output. Do you understand the problem statement or not? I told you this is a comparatively complicated problem. It's a bit more involved, but first, the most important thing and the first is that you should understand the problem statement. Do you understand the problem statement? Okay. Now let's move ahead. Okay. So we need to find out the power output. Okay. Look, output. There is a relationship between input, output, and efficiency. Yeah, efficiency is output over the input, right? So efficiency is basically output over input, right? So output here is the P, power produced, right? This is what we need. Okay. Now input is what? Input is the amount of energy which falls on the silicon layer. So 7% reflected, 10% absorbed in the glass, so 83%. All from the 700. So 83% is the input energy which is falling onto the solar collector, right? So let's talk about the input. So input will be what? Input will be 0.83 multiplied by the original irradiation G, but G is given, what's the unit of G given? It's flux, okay? It should be in watt, right? Because power you will get in a watt or kilowatt. Yeah, by the area, okay? So it's given that the chip is 1 meter long and 0.1 meter wide. Photovoltaic panel, if you see from the top, 1 meter long and 0.1 meter wide. So you know the area, okay? So let me call this, multiply this by L and W. So that's the input. Is it clear? That is what you need to find, right? This is efficiency. Efficiency is what? 0.553 minus 0.001 TSI, right? If we know TSI, our problem is solved. We need to find P. We know G, we know L, we know W. We need to use TSI. If we for the TSI, you need to do a lot of many things. There is no easy way of finding.
That's why it's difficult.
Yes. Do you understand the problem here? You need TSI. If you know TSI, that's it. Then you can find P. P was required. Okay. Now finding the temperature of the silicon chip, now you have to enter into the heat transfer circuit. Now you have to make a heat transfer circuit and enter into that. So let's make the heat transfer circuit. Okay, one thing is clear, that the heat is coming from the silicon. What are the directions where heat can go? Up. Even down is insulated. It cannot go down. Heat has to move up. Okay. So so all the layers below silicon chip are useless for us.
So the last layer is the heat will touch it is the silicon?
Yeah. Yeah.
It will be absorbed.
Yeah, so the thing is that below silicon layer, heat cannot flow. Where there is insulation at the after substrate. The only way heat can flow is going up. Okay, so the thing is that the layers below silicon chip is useless for us. So we'll consider silicon chip as the last layer for our consideration, and this is the T silicon. TSI is what we need. Okay. So we'll have a resistance, conductive resistance within the silicon chip. Is the thickness of silicon chip given? A very thin layer of silicon. So it has no thickness, right? A very thin layer of silicon within the zone will convert to this. So no thickness given. So silicon layer has no thickness. Okay. So but TSI is there. That's the silicon. Okay, above silicon chip, what we have? We have adhesive, right? For adhesive, thickness is given? 0.1 millimeter thick optical grade adhesive. And K value is given. So you don't need to use, or you cannot find it from the table, because K value is directly given. K is given, thickness is given, L upon Ka. That's the thing. Okay, so you have conductive resistance, and this is for the adhesive, right? And it will be L upon Ka, right? Above that you have what? You have the glass, okay? And the glass has thickness? 3 millimeter thick, ceria doped glass, okay, good. And K value is also given, so you will have a glass here. Okay, we can say that this temperature, the top of the glass temperature is Tg top, and the bottom of, we can say Tg bottom, bottom of the glass, top of the glass, right? And it will be what? L upon Ka again, right? Okay, after the glass, what do we have? Then we have radiation and convection, and they should be parallel. Right? So T surrounding, T infinity, right? And they are equal, but for T surrounding, this will be 1 upon HRA. T infinity, it will be 1 upon HA. Is it clear? H is given, right? H is given. And okay, HR is what? Epsilon, sigma, T of this T surface, or like can say, or you can say this is basically Tg top. HRA. Okay, so it's Tg top plus T surrounding into Tg top square plus T surrounding square, right? We don't know Tg top. We know T surrounding. We don't know T top. We know epsilon. We know this. Okay. So now this is the case, and we know T surrounding, we know T infinity, and we don't know anything else. And the main thing that we need to find is TSI. If we find TSI, we can find what is P. So far till here, is it understandable or not? Yeah. Okay. Now what we do is that let's first make an equation between TSI and TG top. Let's first make an equation between this. Okay. So,
Because the Q will be from down or up.
hmm?
And then the bottom to T before.
Okay, now the thing is that we have heat is coming from the silicon and it has to go out. Okay, heat is coming from the silicon, it has to go out, and so from TSI to TG top, how much is the heat which will be flowing? First of all, the heat amount will be same. It's a series circuit from TSI to TG top. It's a series circuit, but the thing is that how much is the heat amount? Look, this is the amount of energy which falls on the silicon layer, right? This is the amount of energy which falls on the silicon layer. And now, if this much amount of energy falls on the silicon layer, then how much is the power produced? The power produced will be P is equals to efficiency multiplied by 0.83 GLW, right? This will be the power produced, right? Now, that was the total. Now, this was the total amount of energy falling on the silicon. This is the power produced. So, the difference between will be the amount of heat. 100 energy was coming, 80 was used to produce electrical power, then the remaining 20 is the heat. Is it clear?
7 or the 10 together.
Okay. Now, to 10 will come when you have the heat rejection from the top. Right now, we are moving from T silicon to the TG top. At the top surface, 10% is absorbed. Okay. So, the thing is that what will be the amount of heat flow from TSI? First, let's try to find out the amount of heat flow from TSI to the TG top. Okay. So, it will be so it will be total coming minus electricity produced. Total incoming minus electricity produced is the amount of heat which is flowing up. Once again, total coming to the silicon chip minus electricity produced is equals to the amount of heat which is going to flow up. You understand this statement or not? Right now we don't know the electricity produced, but we know there is some electricity produced. We know this is the total input energy falling on the silicon chip. This energy is used to produce electricity and heat. So, if you minus the electricity production, then the remaining is heat. And this is the heat which will flow from the silicon layer to up. Is it clear? So, total was 0.83 GLW minus electricity produced. Electricity produced is P, which is efficiency into 0.83 GLW. Okay. So, minus efficiency into 0.83 GLW. Is it clear? Is it clear? This is Q. Or this is the heat. So, this is the heat flowing is equals to the temperature difference from TSI to TG top. Okay. So, TG top minus TSI divided by the resistance in between. And what are the resistances we have in between? Two resistances. L upon Ka for the glass plus L upon Ka for the adhesive.
I think it's a flux.
Hmm?
Flux, no air.
It is no right now it is area, because area is involved. We put LW here. Okay. Although, do you understand this equation? This is the first equation. Now read here. 0.83 GLW minus efficiency 0.83 GLW is equals to T silicon. Oh yeah, sorry, this is my mistake. Heat is flowing from silicon to the top. So TSI minus TG top, right? Divided by L upon K plus divided by L upon Ka divided by L upon Ka. Okay. Now A is LW, so it can cancel. Area can cancel. But anyways, this is one equation. Now here in this equation, again the problem arises is that efficiency involves TSI. We don't know TSI. We also don't know TG top. Neither we know TSI nor we know TG top. The two things are unknown. This is unknown. This is also unknown. And within efficiency, you also have TSI, which is unknown. So you have two unknowns in one equation. Still, it is not solvable. Important thing is that, first of all, do you understand how we made this equation? Okay. Again this equation. Look, if we consider from silicon to the top of the glass, you have the heat flowing. This is the only heat which is coming from the silicon layer. Okay. But we need to know how much is the heat. So for finding out how much is the heat, the logic is that the amount of energy coming onto the silicon layer is converted into electrical energy and heat. So if we subtract the electrical portion, then the remaining is heat. So this is the amount of total energy coming to the silicon layer minus this is the electrical energy produced is equals to delta T upon total resistance in between the two. Is it clear?
Now we have to find another, because we have two unknowns, so we have to find.
We need another equation. Okay. Now we can develop an equation between TG top and outside. Now one thing one can think that why didn't we not directly develop equation between TSI and outside? Why did we do in two steps? The reason is that in between, now when we consider TG top to outside, now there are two type of heat flows which is going up. One coming from the silicon chip and the other which was 10% absorbed in the within the glass layer. So these two both are going to go up now. Is it clear? So that's why we cannot do it in one step, because it's not the same heat which is flowing. At this point, heat is being added, some more content is added into it. Okay. So we have to do this step separate and then this step separate. So first of all, the first step, is it clear? Okay, but it has two unknowns. It's still not solvable. Now let's talk about another step in which we have from TG top to upside. Okay, if we consider between TG top to up, okay, so now in this case we have what? Okay, we have heat flowing. Now how much will be the heat flowing? Heat flowing will be whatever was coming from the silicon chip plus the 10%. Okay. Now whatever coming from the silicon chip, I can do it like this. I can write it as 0.83 GLW into 1 minus eta. I just made it like this, compacted it. Anyways, but this is the component which is coming from the silicon chip. Is it clear? This is the component which is coming from silicon chip. Then this thing, along this I have to add some more, which is the 10% of the input which is absorbed in the glass. Okay. So 0.1 multiplied by GLW, 10% of the input which was coming. Okay. So this is now added. So this thing is equals to Now we have between this point to this point. Okay, so we have T Tg top minus let's do it separately, although they both are equal, it doesn't matter. So Tg top minus T surrounding divided by resistance for this is 1 upon HRA, okay, and plus Tg top minus T infinity divided by 1 upon HA.
Okay.
Is it clear? Now in this case, again we have in this equation we have TSI coming, right? And this TSI is unknown. Tg top is unknown, T surrounding is known, T infinity is known. Okay, HR will have Tg top, which is unknown, and we have H is given. So now again this equation has two unknowns, Tg top and TSI. This equation also had two unknowns, Tg top and TSI. So simultaneous solution of the two equations will give you TSI. Once you have TSI, then you can substitute here and find out the power.